My name is Antia Lamas Linares. I'm the lead for the AWS Center for Quantum Networking. And not surprisingly, I want to tell you about what's going on in quantum networking at AWS. So first of all, I want to spend some of my time talking about what quantum networking is, because this is a very computing-focused conference, and obviously it's not the subject that you've been hearing about for the last 2 days. Also, I want to tell you why we care about this subject, and what we are doing in this space. Clicker. All right, clicker doesn't seem to work. It was, but it is no longer. But it is no longer. I don't know. Maybe somebody can switch to the next slide. Okay, so to give you some context, quantum technologies at AWS, it's actually we have a pretty broad portfolio of quantum technologies. You've been hearing about these for the last couple of days. Whoa, now it went ahead. Okay, well, you've been hearing about these for the last couple of days. We have a few things going on. One of them is the bracket service, which gives customer-facing access to quantum computers. So those are third-party hardware providers. People can access them in the same way that you would access like an EC2 instance or, there we go. No worries, thank you. You also have heard about the Amazon Quantum Solutions Lab, which is essentially a consulting arm where we help customers develop quantum solutions with the help of subject matter experts. We've also talked about our Center for Quantum Computing, where we develop quantum computing hardware under Oscar Painter. Well, our last entry on these quantum technologies is the AWS Center for Quantum Networking, where we develop technologies, hardware, and applications for next-generation quantum networks. And the idea there is that these things have applications in secure communications, in obviously linking quantum resources eventually, and so on. We were announced in June of this year in a blog post in our quantum computing blog. The TLDR of that is that we are doing hardware development, we're doing exploration of the applications fit to the AWS network infrastructure. We're based in the Boston area, and we also have a close collaboration with the Harvard Quantum Initiative, and this takes the form of some sponsored research. We recognize that there's still a lot of work to be done in the area of quantum networks, a lot of fundamental science that is best tackled probably in academia, so we have a sponsored research agreement there. We've also enhanced and upgraded their nanofabrication facilities for use of ourselves, but also of the rest of the quantum ecosystem in the Boston area. And finally, we also have a big interest in developing the next generation of quantum engineers and scientists, and that takes the form of a scholarship program. And that's not just dedicated to quantum networks, by the way. It's broadly quantum information, quantum technologies. So to put things into context, again, for this audience that is mostly familiar with quantum computing, I want to make sure that people realize that this is not quantum networking is not a new thing. Actually, it has been more or less co-evolving with quantum computing for a few decades now. So I have a little timeline there with some milestones that are not random, but there are a certain selection. And color-coded with quantum networking in orange and quantum computing in blue. And you can see that quantum networking started arguably with something called quantum money in the 70s. I don't think anybody paid much attention to that, but that's sort of where origins come from. Then in the early 80s, things start to get a little more interesting. We have the first ideas about quantum simulation. For quantum computing, we have in quantum networking the first protocols for what was called at the time quantum cryptography, BB84, a way to share private randomness between two parties using the properties of quantum systems. That was evolved into an entanglement-based protocol in the early 90s by Arthur Eckert. Then in the mid-90s, again, things start getting very interesting for quantum computing. Everybody's favorite algorithm, Shor's algorithm in 94. 95 sees the proposal for the implementation, how to implement a universal quantum computer in ion traps, the DiVincenzo criteria for what makes a useful quantum computer. And this was well before anybody had anything that could really be called a quantum computer. Then we go to 97. That's a big milestone for quantum communications with the experiments on quantum teleportation. And you're all probably all familiar with the fact that this year the Nobel Prize was given to people for development and exploration of entanglement. And this was one of the landmark experiments of use of entanglement by Anton Zeilinger and his group and other people in Rome simultaneously. Okay, then I take a big step, and now we're entering we're still in quantum computing in this NISQ era that we've been hearing all about in this last few days, which arguably starts with, the ideas about boson sampling and complexity there. And I guess you can blame Scott there in the back for that. And for quantum communications and networking, a big milestone was the launch in 2016 of a quantum-capable satellite by Chinese researchers. So this was a satellite that had quantum payloads on board. It was able to do quantum key distribution from satellite to ground, able to do entanglement distribution, and several other very interesting capabilities. Like, they've been essentially churning out experiments every year since the launch, and now they launched some more satellites. And of course, everybody knows in 2019. The quantum supremacy experiment by Google. This is just to give you a sense of where these things, how these two areas have been leapfrogging each other and sort of complementing each other. And of course now we're at I would claim, the small furry mammals stage of quantum technologies, where we have a lot of very interesting, maybe not quite useful things coming along, but they're definitely showing promise. All right, so what is quantum networking? Without attempting to do a formal definition, it's the transfer, routing, storing, and measurement of quantum states over significant distances. Now, typically when we transfer these quantum states, these qubits, it's going to be photons, just because photons are really good and they're really fast, and they don't care that much about their environment, which is always a very good property when you want to send them across maybe a hostile environment or a not very well-curated environment. And you can think of quantum networks as having a few definite steps in complexity. The first one would be just the transfer. You send a qubit from A to B. That's really easy. Just a single photon, down a fiber, down a free space channel. Next, you could argue distribution of entanglement. So for that, you need to generate entanglement. You need to send it to two places. And then things start to build into the improving the efficiency and the complexity of what you can do. And for that, you need things like storage of qubit, quantum memories. You need joint quantum measurements, heralded measurements. And finally, you need quantum transduction if you want those flying qubits or photonic qubits to talk to things like superconducting qubits, potentially. Some of these technologies are sort of bundled together in what we call quantum repeaters. And that allows you to build these complex quantum networks. To give you a sense of what the technology timeline might look like, this is very, very rough, don't take it too seriously, but on the bottom you have enabling technologies, and on the top you have some applications that are interesting. So today you can already do what we call trusted node quantum key distribution, which is useful for quantum safe encryption. In a few years, you would expect to be able to distribute entanglement to any 2 points in a large network and have things like trustless communication. And finally, as the roadmap converges with quantum computing, you would get things like secure delegated quantum computing and things of that sort. All right, so why do we care? What is it that we're trying to do? And if you saw the talk by IBM about quantum security, you already know a lot of this. But the background is that quantum computers via Shor's algorithm can break the way we do encryption today. So there's a particular part of the crypto stack that is vulnerable to quantum computers, to sufficiently large quantum computers, or cryptographically relevant quantum computers, and therefore we need to care about this. Now, of course, those quantum computers don't exist yet. They're actually pretty big to run Shor's algorithm in a relevant way for cryptography. So a time horizon for breaking, say, RSA is estimated maybe 20 years, and that has a huge error bar. You know, we just don't know, but that's a reasonable way of framing it. The problem is that we need to care about this now, and we need to care about this now for two reasons. One of them is that cryptographic systems take notoriously long to update. They're just, even in the best of cases, they take between 5 and 10 years. We know this already. And many data types have useful lifetimes of more than 20 years, more than 30 or even 50 years, because we have things like health data or classified data. And we don't want that to be vulnerable. The problem is that somebody can record that data today and wait until the computer becomes available and decrypt it later. There is not a no cloning theorem for classical data, so people can copy it and reproduce it. Mitigation of this is, of course, to use some kind of quantum-resistant encryption, and there are several forms of this. So let's talk about this, and luckily I hopefully don't have to go too much detail into this, but one of them is post-quantum cryptography. And the idea here is that we have classical cryptography, or what we use today, uses trapdoor functions that are very easy to compute in one direction, very hard in the other, and that is the basis of their security. That breaks down with existing cryptography because of Shor's algorithm, but we can come up with new algorithms that are based on different computational assumptions, and we can replace these things. And that is going on today. There's a competition by NIST. So there's a lot of work in this area. There are a lot of advantages to this. It's a software solution. It's kind of available today. It's flexible, upgradable, easy to virtualize. All of these are fantastic things. It's a little bit, one of the problems, potential problems, is that there's no proof that these things are secure. So if for whatever reason that algorithm was vulnerable, or we made a mistake in designing it and nobody caught it, and data got encrypted with that and recorded, and we found a problem 10 years later, that data becomes instantaneously exposed. So that's not a good thing. Of course, there can be backdoors, errors, and intentional, just errors and intentional. You know, history is full of examples of these things. Just a note to say that AWS is heavily involved in PQC developing and testing. You can actually opt into using post-quantum crypto algorithms in the AWS infrastructure, if you so wish. But again, one has to take these algorithms with a little bit of caution. You know, just recently, one of the very close to finalist algorithms in the NIST competition was shown to have a fundamental flaw, and it was broken not by a supercomputer somewhere, it was broken in a laptop in an hour, and that was after years of scrutiny. So that's worrying. All right, what about quantum key distribution? Well, quantum key distribution is very, very different. You know, they kind of sound similar, but it's a completely different way of searching for this quantum security. First of all, it's a physical method to distribute keys. This is maybe neither good nor bad, it's just a statement of fact. The security of the keys that are shared can be rigorously proven. So there was a lot of work in the last few decades. There are mathematical proofs of the security. It's also a security that does not depend on advances in computational power or cryptanalysis or anything like that. It gives you that future proof in that sense. Also in the sense that if there was a flaw found in the QKD system, it's either broken at that time or it cannot be retroactively broken. On the minus side, and this is a very important minus, is that it requires dedicated hardware and compatible networks. The compatible networks is not such a big deal, but dedicated hardware, of course, requires a change of what we currently have. And just a final note, there are, side channels are possible. Despite that proof of informational security, that relies on assumptions. If those assumptions are not correct because of the way of the system was implemented, obviously this doesn't stand. And that's not different than any other technology. All right, so I'm gonna go through this very quickly, but a note about how we approach security. So we never approach security as something that comes in a single layer. We approach security with a posture of what we call defense in depth. And that is the idea that you never rely on a single layer or a single process to secure all your information. And this is not a quantum thing, this is just a general thing. And an example is how we layer end-to-end encryption. So you see there are two data centers, data center 2, data center 1, and there's a connection between instances in the data center. And you might encrypt your data as it leaves, the first computer, goes through the data center, exits the data center, goes back in, and only gets decrypted at the very end. You have end-to-end encryption, and in principle, that should be sufficient. You don't really care what happens in the middle. But in AWS and in many other places, as that aggregated data leaves the secure perimeter of a data center, it gets re-encrypted. It's called a link encryptor, and it just adds another layer on top of that end-to-end encryption. If you think of this in the context of quantum security, you could think of layering, for example, post-quantum cryptography in quantum key distribution. When you think of defense in depth, you would like the threat model to the security of those layers to be as distinct as possible. And this would give you that kind of security as far as the quantum, cryptographically relevant quantum computers are concerned. All right, so switching gears now, what are we actually doing? So all of that was introduction. So first, let me tell you a little bit of some of our latest research. So this is work we've done with our collaborators at Harvard. It was published in Science very recently. And the title of the paper doesn't really tell you what I'm going to tell you about. It says, multi-qubit quantum network with integrated error detection, which is great. You should read the paper. But what I want to tell you is that one of the things that has us most excited is that typically the platform that we're looking at, which is silicon vacancies in diamond, has to be run at really low temperatures. That means in a dilution fridge, which are the candelabra sort of steampunk things that all the superconducting quantum computers are in. And those things are, A, very expensive, B, they require sort of a dedicated cohort of acolytes keeping them running and taking care of them. And while that is okay for a quantum computer, that is a very powerful device that might site it in one location, it's not an ideal model for a quantum network because you're not going to be deploying dilution fridges every 50 kilometers in a wide area. That's not scalable. So we were very excited that in this paper we were able to show these devices running not at millikelvin temperatures, but at Kelvin temperatures. And that, although 1 Kelvin or 1 to 4 kelvins is still extremely cold, it brings you up to a completely different refrigeration technology. And it's at least an order of magnitude cheaper, it's rackable, you can put it on a rack, and it just reduces the complexity immensely. So this is some of the kind of things that we're looking to do. How do we increase the TRL level of these systems so that they become really practical, really deployable, and something that we should be integrating? All right, and switching, so that was part of our research, and then a taste of what we're doing with commercially available devices. And Joe Fitzsimmons at Horizon yesterday teased a little bit about this, but we are both Horizon Quantum Computing and us are part of a consortium in Singapore that is deploying the National Quantum Safe Network, NQSN. So this is a nation-scale quantum network in Singapore. Singapore is an ideal place to do this because it's kind of small. The maximum distance in Singapore is about 60 kilometers from one end to the island to the other. Anyway, so ideal place to test these kind of things. And what we did with Horizon was connect their site to another site that is physically based at the National University of Singapore, but that is equipped with essentially AWS cloud devices. So these are cloud in a box kind of devices that stand in for AWS and have pretty much the same capabilities. You can run, your containers, your VPNs, VPCs, anything you want, and it looks exactly like the AWS cloud. So this is a first step towards connecting a end customer to a customer to the capabilities of AWS. And this allows us to really take these first steps, evaluate the infrastructure, collaborate with academia, industry to really extend the reach of these things. This is very briefly what it looks like. I won't go through all the details, but there's a commercial QKD system. And what we're doing is the simplest possible thing you can do, which is do a link encryption of the communications between Horizon and this AWS mini cloud, if you like, and set up some IPsec-based protocols like a VPN and so on. So this is for those of you that are used to networking. It's OSI layer 3. Actually, there's an error in that slide. And just to give you a little bit more background, and this is the last thing. This AWS edge devices are essentially tamper-proof boxes. They look like old-style computing towers, and they're extremely rugged. You can literally check them in your luggage and send them somewhere, but they contain all of this AWS infrastructure within. And with that, thank you very much.
Sir, we'll have to just run back and forth.
Thanks for the talk. I think that's great stuff. But I also wanted to ask, too, is your team looking at satellite QKD at all?
Sorry about that. No problem. So thanks for the question. Yeah, that's a very relevant question. I'll say one thing. AWS has data centers all over the world. At some point, if the objective is to distribute entanglement to every point in the network, satellite QKD will probably come into the picture. Even with quantum repeaters, you're probably not going to put, quantum repeaters every 50 kilometers in a submarine cable. I think we're still far from that level of development, even with remarkable cryostats.